This is the video number 7 in the series of concrete reinforced slabs. Let's look at the free edges of concrete slabs. They always need a reinforcement in a U-shaped rebar just to close off up the edge of the slab. The length of this U-shaped element is at least 2 times the depth of the slab. The U-shaped corner reinforcement can be, in general, be put as mentioned here. It's on the outside. In the second layer, it's the main reinforcement, and the secondary reinforcement is on top of that. But in fact, you have two different options. You don't need to use all those different layers because a slab is normally like 200, 250 or 300 millimeters, so you do not have a lot of space. So when the main reinforcement, you can put it in the second layer, and the secondary reinforcement is in the first layer, but in the same layer as the U-shaped corner reinforcement. So that's an improvement, that's better. You avoid buckling out of the main reinforcement because now it's trapped within the secondary reinforcement. But for slabs, because they are so small in depth, we want to use a maximum effective depth so that we have the least amount of reinforcement. And in this case, when the main reinforcement is in the first layer, then you can put the secondary reinforcement on top of it and the U-shaped reinforcement on top of it. Now for free edges, U-corner reinforcements, you need it for all slabs. You may not forget it. The U reinforcement in the X directions should be placed in the same layer as the reinforcement in the X direction, preferably. And all faces need to be reinforced. All faces of the concrete need to be enforced. And all reinforcement must be sufficiently anchored. Now we can have a quick look at the shear force. Shear force in slabs, in fact, the shear force in slabs is two-dimensional, and then we call it punching, and that video 15 will deal with punching shear reinforcement. This is now the shear reinforcement for a one-way slab, and it's treated exactly the same way as for beams, but then for a section with 1 meter width. There is one big difference, that for continuous supports, you only need shear reinforcement if the acting shear is bigger than 1.25 the resistance of the plain concrete in shear. So you have a 25% bonus. And for all the rest, it will be exactly the same as we treated beams. Now, shear reinforcement in slabs is a complicated thing. We can think pure theoretically about the shear reinforcement doing that with a precast slab, and the shear reinforcement is already in there, and then in a second movement you can complete the pouring of the concrete on top of it. But this is not very practical. It can be done, but it's not very practical. Placing stirrups in a slab, you can see immediately if this is in this direction the main reinforcement, then you need a certain spacing rule in this direction. You need a spacing rule in the second direction. It is rather complicated to achieve this and a lot of labor to achieve that. And stirrups, it's in fact not possible when the depth of the slab is smaller than 200 millimeters. Then you can only use bend up bars instead of stirrups. So we can conclude that you should avoid shear reinforcement in slabs at all times. Make the slab thick enough or make the concrete grade bigger, but avoid shear reinforcement in slabs where possible. This is a bend up bar. It is possible. It can happen that at the support you have a large shear force and you have to take it up with additional reinforcement. Then use your reinforcement needed for bending, and at the end you just flip it over so that this bar can be used for shear, to take over shear. Then something about minimum and maximum reinforcement. The minimum reinforcement for brittle failure is exactly the same as for beams. Now for slabs we can fill in some values, and when FAK is equal to 500 megapascal, then this formula becomes this, which means the minimum reinforcement is 0.156, the concrete grade to the power 2/3. And it must always be bigger than 1.3 times the effective depth of the slab. This is because B here is 1 meter. To simplify it, for a concrete grade of C3037, the minimum reinforcement is 1.5 times the effective depth of the beam. Now, the dimensions are right because it's multiplied by 1 meter width. So it is square millimeters, in fact. D is a millimeter, and then you have square millimeters. For crack control, the minimum reinforcement for crack control, exactly the same as for beams. We can see now that the factor Kc is the same as for beams, is 0.4 for bending. And when we use the steel stress equal to the FAK, then you can rework those formulas a little bit. And I'm defining A0, the basic minimum reinforcement for crack control, at 0.12 times FCK to the power 2/3 times the total depth of the beam, FCK in megapascal. And the factor K0 depends, it's a dimensional factor. It depends on the height of the slab, according to these formulas. And now this can be converted into a simple formula like that. Example of restrained deformation of a slab. We can use this formula for that. For pure tension, Kc is 1, and the area in tension, when it's a restrained deformation, it means that the total area is in tension, so it's B times H, or it's 1000 times the total depth of the slab. The steel stress equals to 500 megapascal, because I'm not concerned here with a limit on the crack width. And the concrete tensile stress, yeah, this is the FCTF. This should be the resistance of the concrete to tensile stresses at appearance of the first crack. But we do not know that. So FCTF is most of the time taken as the mean value of the tensile strength, which is FCTM. Or if you don't know, we just take 3 megapascal in normal cases. And when you apply this formula, then this becomes this formula, which is very easy. The splitting up of the formula is because of that factor K, K, which is different in different cases depending on the total depth of the slab. Remember, we have chosen here ACT as the total area. It means that when you calculate the minimum reinforcement, the amount that you have, you divide it by 2, and that is the portion put in the bottom and on top. So it's always, when you compare minimum reinforcement, don't forget that for restraint deformation, you put half of it on top and half of it on the bottom. For crack control, we have this equation. For brittle failure, we have this equation. Now we can easily see that when the effective depth is bigger than 0.77, the total depth of the slab, then brittle failure is dominant. So that means that in a lot of cases, brittle failure is dominant. This formula is dominant. There's also a maximum reinforcement, and the maximum reinforcement is 4% of the total concrete section. For slabs, it means that if you use units square millimeter per meter and millimeter, you see that the maximum reinforcement is 40 times the depth of the slab. Crack width calculations is exactly the same as for beams. Just a small reminder, the crack width is always the delta epsilon multiplied by the maximum distance of the cracks. So the SR max is the maximum crack spacing, and the epsilon SM is the mean steel strain, and epsilon CM is the mean concrete strain. And this delta in strain between concrete and steel can be written as this formula, with KT is a factor which is 0.6 for short-term loading and 0.4 for long-term loading. FCTF, like we said before, we can take it as FCTM, the mean value, and it's 0.3 times FCK to the power 2/3. Alpha E is ES divided by ECM. It's the modulus of elasticity of steel divided by the mean modulus of elasticity of concrete. The effective reinforcement ratio is the tensile reinforcement divided by the effective concrete area around the reinforcement. And the effective concrete area is the smallest of B, the width, times h minus x divided by 3, b times h over 2, and b times 2.5 h minus d. SR max then is equal to this formula. When you have different diameters of reinforcement in the same section, then you have to take an equivalent diameter. K1 is for bond, so it means 0.8 for high bond and 1.6 for plain rebars. And K2 is a factor which is giving you the stress redistribution in the section, and K3 is 3.4. It's a calibration factor, and K4 also a calibration factor. And C is the concrete cover. Take care, this is not in fact the actual concrete cover, but the minimum desired concrete cover, C0. When there's a difference between the minimum desired concrete cover and the actual cover, then you can increase the maximum allowable concrete width by this simple proportional formula. Then we have the factor K2, which is dependent on the strain, epsilon 1 and epsilon 2, and epsilon 1 is the greater strain and epsilon 2 is the lesser tensile strain at the boundaries of the section considered, assessed on the basis of a cracked section. So it's the tensile strain on the boundaries of the section considered. So it's at the bottom and at the top, and epsilon 1 is the biggest one. If this is bigger, then this will be epsilon 1. It's just a definition to arrive at this formula. Now, in fact rather simple. For pure bending, epsilon 2 is then of course 0, and epsilon 2 is 0, then you see that K2, this factor is a half. This is for pure bending. And for pure tension, epsilon 2 is equal to epsilon 1. And if you fill it in this formula, you see that for pure tension, this term is 1. SR max is the maximum crack spacing. We have seen that this is the formula for it, but there's a reduction, or there's another formula, a correction of the formula when the spacing of the bars is too big. And this is quite commonly quite common for slabs. So if the center to center distance of the rebars is bigger than 5 times the cover plus the biggest diameter divided by 2, then you should use as SR max this formula here, well, sorry, this formula here instead of this formula. Something about stresses. In ultimate limit state and ultimate limit state persistence, then the maximum allowable stress in steel is the yield of the steel divided by 1.15. For the concrete, it is 0.85 FCK divided by 1.5. The 0.85 is alpha CC, and in some countries alpha CC is 1, but in Belgium the alpha CC is 0.85. In accidental situations in ULS, then we know that the steel will be equal as FAK, and the concrete will be equal to 0.85 FCK divided by 1.2 instead of 1.5. And ULS temporally, it will be the same as ULS persistent. In the serviceability limit state, in the characteristic serviceability limit state, this maximum steel stress is 0.8 FAK, and for the concrete is 0.6 FCK. But we should be aware that in SLS characteristic, when the environmental, or when the class is XD, XF, or XS, then the concrete stress should be limited to 0.5 FCK. In serviceability limit state frequent, then we also have the steel maximum steel stress 0.8 FAK and the concrete 0.5 FCK. And in SLS quasi-permanent, we have also 0.8 FAK, but when we have the restraint deformation, it will be FAK. And then in SLS Q quasi-permanent for concrete, the maximum concrete stress is allowable stress is 0.45 FCK.